Good morning to everybody. First of all, I would thank the organizers for the organization of this workshop, which is very interesting. Actually, referring to one of the last slides shown by Stephen Hoffman, I really think that this graphene is one of the exemplary systems where you can have a continuous bridge between fundamental science and eventually industrial applications. Because there is really a continuous path between fundamental science, applied science. I mean, we have seen several things in these days. Yesterday, today, and we will see further applications. I move towards some fundamental aspect. And the fundamental aspect is to use molecular self-assembly onto graphene to get some, I call them advanced functionalities. Why do we use organic oligomers at surfaces, and in particular on graphene? If you use atoms and you absorb atoms on a surface like cobalt, which presents a magnetic moment, usually what happens, cobalt absorbs on metals as single atoms. Then when you increase the coverage, the atoms tend to aggregate and to form clusters. So in a way, diffusion and cluster formation hinders the possibility to use metallic atoms as, let's say, single magnetic units to be potentially applied. One need to use magnetic center is to have some sort of long-range ordering. On the other hand, we know that there are a few molecules, organic molecules, which are embedded where you have magnetic atoms embedded into an organic cage. And with these organic molecules, this is an example I will show afterwards, which is metal phthalocyanines. You have a single magnetic unit into a square-shaped organic cage. And so the idea is to build up a sort of spin network, an organized spin network, where you don't have clustering and where you can keep and maintain the single magnetic unit. I will skip this slide on graphene because we heard a lot about graphene. So my purpose is to, in a way, to assemble molecules in a controlled way by controlling the deposition, by exploiting self-assembling. And of course, self-assembling is driven by the specific substrate you are using. And in these ways, one would like to control the building up of the nanostructure and control also the electronic, magnetic, and transport properties. Now, which is the molecule we are using? It is iron phthalocyanine, or in general metal phthalocyanines. You have some sort of pi-conjugated rings, which is the organic cage, and in the internal part of the organic cage, you have a single atomic metal atom. These, I mean, there are tens and tens and tens of synthesized molecules like this. So it's a very easy molecule to have. And the main point is that we use this organic cage as a, let's say, van der Waals or a chemical graft to the surface. Here again, I show the cobalt example. If you have a single cobalt atom, you have a rather high magnetic moment. Then you approach the surface. Then you build up a cluster and then eventually a layer of cobalt. But the magnetic moment lowers and you lose, in a way, the magnetic information, or at least the possibility to control the magnetic information. And here you have an experiment, a recent experiment by the group of Nick Brooks in Grenoble, where you actually grow cobalt on graphene. But these single magnetic atoms, you can see they cluster and then they eventually form crystals, cobalt crystals. What happens with iron phthalocyanine? Here we have two different graphene substrates. One is grown onto iridium and this is grown onto ruthenium. And these are STM experiments by two different groups using cobalt phthalocyanine and iron phthalocyanine. They're not very different each other. I mean, there is, of course, a different orbital occupation and a different final spin, but they're not different, very different each other. You can clearly see that these molecules, they really build up an ordered array. In one case, it is some sort of square-shaped ordered array, and in the other case, it is a trigonal-shaped ordered array. So in both cases, you have a very highly ordered array, and in this way, you may try to use these single spots as single spins. Why they have this different configuration. We know, it has been also shown that depending on the metal substrate where you grow and you prepare by chemical vapor deposition graphene, you have a different lattice constant and at the same time a different height of graphene with respect to the metal. So the misfit in lattice constant determines the well-known moiré effect. This is a real space image. This is a reciprocal lattice image. And you do get a very ordered superstructure. And this superstructure is due, of course, to the mismatch. And it presents two effects. On one side, there is a geometric effect, which means different height in different positions. On the other hand, there is also a different electronic configuration in the sense that there is a different electronic distribution of states. That's also an experiment where you can see that depending on the metal graphene, this is a carbon 1s core level, you can see that the almost freestanding graphene is available onto platinum and to iridium. But on platinum, the interaction is so low that you get some sort of natural corrugation and disordered natural corrugation, while onto iridium, you do get this moiré configuration, which means a higher interaction, but at the same time, the interaction is not so high to change the electronic properties of graphene. So the moiré and the corrugation is the explanation of these two different configurations. In fact, onto iridium, you have an almost freestanding graphene, and the molecules tend to assemble mostly because of molecular interaction. In fact, I don't show them here because I don't have time, but there are density functional theory calculations performed by the group in Trieste, Stefano Fabris and co-workers, and they show that, let's say, the natural configuration of a single chain of phthalocyanine is this kind of configuration, where you have a line of molecules with the sides with a small angle between each other due to the better overlap of the hydrogen atoms. So this configuration is basically driven by the molecules, and the role of the moiré is a minor role. In this other case, graphene and ruthenium, there is a very strong carbon-ruthenium interaction, and this interaction gives also a strong moiré corrugation and a strong effect of the electronic states due to the metallic substrate. And as a matter of fact, the moiré drives the regular configurations because you have a trigonal lattice. Actually, this is a known lattice. It's the Kagome lattice, which is basically due to the substrate. So you have two different configurations, but both are ordered configurations. Now, we grow graphene through the well-known chemical vapor deposition method. First of all, we deposit phthalocyanine. First of all, we have to check the order. The order is still there, so phthalocyanines are not destroying the long-range order. Second aspect, how are the phthalocyanines oriented with respect to the substrate? This is an X-ray absorption experiment on the first single layer of phthalocyanine performed with linearly polarized radiation. So we are sensitive to the molecular orientation if the molecule is oriented. And as a matter of fact, we have a strong dichroism. This is the nitrogen K edge. So you have excitation from the 1s to the pi star orbital. So you have a definite polarity and definite symmetry. And this strong dichroism, by changing the orientation of the electric field vector, allows to say that this layer is very, very, very flat. So it's very, very flat, and the line shape also tells you that there is no strong interaction. So the molecules are flat, they are ordered, but there is not any strong interaction. When you build up a thin film, these are 20 nanometers of phthalocyanine, they still keep maintaining their flat orientation. So you have a way to stack molecules onto molecules in a layer-by-layer fashion. What about the interaction? This is phthalocyanine deposited on bare iridium, and this is the iridium 4F7 core level. On clean iridium, you have a very strong surface core level shift. This is not the spin orbit. The second spin orbit split orbital is there. This is the surface core level. And you see that if you deposit phthalocyanine onto bare substrate, you do get immediately the decrease of the surface core level because there is an interaction. So the phthalocyanine interacts with iridium. But what happens onto graphene and to iridium? You still observe the surface core level of iridium even below 50 angstrom of layers of phthalocyanine. So there is an actual decoupling of phthalocyanine from the metal. And that's important if you want to exploit the phthalocyanine magnetic state. There is a marginal doping of the Dirac cone. This is the Dirac cone of the clean surface, and this is the Dirac cone after one layer of phthalocyanine on top of it. This is a typical molecular orbital of the molecule. You just get a marginal 100 millivolt doping. You get a very ordered, here the picture is not clear, but you get an ordered overlayer, and this ordered overlayer corresponds to the ordered overlayer observed for cobalt phthalocyanine, which is, some sort of square-shaped array. And you also get, for iron of phthalocyanine, a rather high adsorption energy. This is a thermal desorption experiment. In the sense that we are looking at the nitrogen core level. Nitrogen core level is due to the organic cage. And the nitrogen core level is a function of temperature, a linear ramp of temperature applied to the system. And you observe for all kinds of phthalocyanines, iron, cobalt, copper, a first desorption peak due to the multi-layer desorption. Then you leave a single layer onto the surface. And the single layer onto the surface desorbs at much higher temperature in the case of iron and cobalt phthalocyanine, much lower temperature in the case of copper phthalocyanine. You can even get an adsorption energy, and this adsorption energy tells you that iron and cobalt are closer to carbon than copper. So copper is less easily bounded. Now, magnetic response. Pure iron has, for each single atom, pure iron presents this magnetic moment. Iron embedded into phthalocyanine presents a very similar magnetic moment, and this is also valid for the other phthalocyanines. Why does iron still in phthalocyanine present a magnetic moment? This is iron in the atomic phase. Due to the crystal field effect, you have a D4H configuration, so you have a D-splitting of the levels. And due to the occupancy, iron is present as a 2+ ion into phthalocyanine. It has a spin equal 1 configuration. This spin equal 1 configuration is associated to atomic orbitals, which are molecular orbitals, which are basically oriented normal to the surface, so Z-oriented orbitals. On the other hand, cobalt phthalocyanine has as well orbitals oriented perpendicular to the surface, which possess a magnetic moment, and copper phthalocyanine presents as well magnetic moment, but only oriented parallel to the surface. So we have mostly out-of-plane magnetic orbital, out-of-plane, in-plane. But today I will show the main results concerning iron phthalocyanine. How to measure the magnetic response of the molecules onto the surface? By exploiting the selection rules in the X-ray absorption when you have, instead of having linearly polarized radiation, when you have circularly polarized radiation. Because in that case, you are sensitive to the MJ configuration. And so if there is any dichroism by changing the circularly polarized radiation, then there is a magnetic moment different from 0. This is the experiment performed in Grenoble. This is an effect of open office with respect to PowerPoint. So we have an experiment performed with the polarization, the circular polarization, either parallel or anti-parallel to the applied magnetic field. And in these conditions, if the system is magnetic, you get a dichroism. And we do the experiment by analyzing all the orientations from, let's say, parallel to the surface to normal to the surface to see whether there is a magnetic anisotropy. And we do this experiment for a single layer of iron phthalocyanine and 2-graphene, for a thin film, and for comparison, for a single layer of iron phthalocyanine on gold. Why? Because we already knew, and we know, that on gold you have as well very ordered array of molecules, and you can see them both in a microscopy experiment as well as in a diffraction experiment. And on gold, you have a quenching of the magnetic moment because the molecules, in that case, in the case of gold, they rather strongly interact and they mix their orbitals with the phthalocyanine, and this quenches the magnetic response. So these are the results. It's a very complicated image. Let's concentrate into this experiment. So here you have blue means out of plane experiment. Red means in plane experiment. Then dotted and continuous line means parallel, anti-parallel polarization with respect to the magnetic field. So if you observe the in-plane experiment of the single layer of phthalocyanine, you don't observe a strong difference in the absorption spectrum. And in fact, this is the difference. While if you analyze the out-of-plane experiment, you do observe a clear difference into looking at the two polarizations. And this is the difference. So this difference means that here you have a rather strong magnetic response and a rather strong anisotropy when you go from in-plane out of plane. And this is an important effect because if you want to use magnetism, and if you want to put a single bit of information, you must have an anisotropy. If you don't have an anisotropy, then you would mix the information. If you go to, let's look now only this image. If you go to the thin film, in the thin film, you don't get this strong spatial anisotropy. You get the magnetic response, but the magnetic response can be as well oriented in all directions. And so you cannot exploit it in the thin film. And if you go in gold you are quenching the effect because of this orbital mixing. There are some rules by analyzing those data, these data here, L3, L2 absorption, and then by using appropriate sum rules, you can determine within certain approximations the orbital component of the magnetic moment and the spin component of the magnetic moment. And so you can also disentangle the two contributions to the magnetic moment. And this is the effect on the single layer of phthalocyanine, spin component of magnetic moment as a function orientation angle. So this means spatial anisotropy. And you get a strong spatial anisotropy. But you get also a strong spatial anisotropy concerning the orbital part of the magnetic moment. While in the thin film, this one is quenched, and in gold, they are both quenched. So this, again, means you can exploit, in this case, both contribution of the magnetic moment in a highly anisotropic response when you have this single layer onto graphene. Of course, onto graphene, because if you would put it into iridium, you would have something very similar to gold. An interaction, a strong interaction, and the quenching of the response. So this, again, is the, some sort of conclusive slide with this strong anisotropy on the single layer and no spatial anisotropy in the thin film. And this is what happens in atoms. This is a recent paper in Wiesendanger group, and they absorbed iron atoms and cobalt atoms onto monolayer graphene. And as a matter of fact, the magnetic response is much lower than magnetic response observed for the molecules, and you don't have the anisotropy that you observe in the case of iron phthalocyanine. So in a way, using magnetic oligomers allows you to have an ordered array of a spin network. And in particular, when you adsorb onto graphene, decoupling from the underlying metal. What is this, which is the origin of this, of this strong anisotropy? It's not easy, theoreticians are working, but if you use density functional formalism with different approaches to understand the van der Waals effect, you get different results. So it's a very difficult task. On the other hand, if you look at the experimental data, this is the L23 absorption without polarization. This is just linearly polarized. Thin film, single layer. You do have mostly the same response. There is a difference that the lines, the resonances, are much narrower. And narrowing may mean higher correlation. So probably correlation more than breaking of symmetry may play a role in determining this strong anisotropy. So conclusion, we have got almost a spin network of spin states by using iron phthalocyanine and 2-graphene. Of course, there are limitations, and the limitations are these, that it's not written, but I tell you, the critical temperature for the magnetic field to go from paramagnetism to magnetism, ordered magnetic array, is very, very low. It is 6 Kelvin. And so, of course, you cannot work at 6 Kelvin, of course, in real world. So we are, let's say, we are playing again. We are going further. On one side, trying to use other phthalocyanines which have not only a higher spin response, but more, they have a much relatively higher critical temperature. And so the idea is to try to have a system with a higher critical temperature, and this is on one side. On the other side, which is the second aspect, we have to apply a magnetic field if you want to, or otherwise to maintain very low temperatures. Another possibility is to use a magnetic intralayer, and so to try to obtain the ordered magnetic system without applying the magnetic field in remnant conditions. This has been already shown that cobalt intralayer can be intercalated below graphene. There are works showing data, electronic properties, etc., etc. So the following step will be to do it and to try to obtain a remnant effect. I would thank the group in Rome, Simone Lisi, who has done most of these measurements together with Pierluigi Gargiani, who is now at Alba in Barcelona, and Mattias Cardamaglia, who is now at Mons in Belgium. But I would also thank the people who are continuing the work concerning the graphene and molecular assembly and polymerization, who are Lorenzo Massimi and Walid Urgini, and of course, Maria Grazia Betti, my main collaborator, and the collaborations with the theoreticians in Trieste and in Modena, Enrico Calzolari and Stefano Fabris, Silvio Modesti for the STM experiment, and Baraldi and Litzit for the experiment at the Superesca beamline in Trieste, and Nick Brooks for the work at the ESRF for the circular magnetic dichroism. Thank you for your attention.